Welcome everyone to this third session of today. And I have a great pleasure to introduce Brian Conrey, who will talk about twisted moments. You're welcome.
Thank you, Kaisa. Yeah, thank you for this for the invitation to speak and for this nice occasion of Balu's 70th birthday. Wow, that sounds like that's getting up there. I guess we'll all get there soon. Some of us sooner than later. Anyway, I first met Balu back in, I believe it was 1981 in Urbana. So we're talking 40 years ago. Is that right? Well, you were there, Bala, the 81, 82 academic year in Urbana? Or was it 80, 81? It was 81, 82, right?
Yes. Yes.
Yeah, 81, 82. And yeah, he had just recently done his very nice work on the error term in the second moment of the Riemann zeta function. And I was working on zeta function too. So I was very excited to have him. I was at Illinois from Urbana from 80 to 82. So I was very happy that he was going to be there as well. And so that was quite nice. And so we managed to do some work together. And that work is going to sort of form the basis for this talk, which I've called Twisted Moments. Now, I'm going to attempt to do it's mostly just in slides, but I thought I would try to do some writing as well. And let me see if I can manage that just to get warmed up here. And so let's see if this works here. So let's see. So what do we mean by twisted moments? So I'm going to be interested in things like integral 0 to t, zeta half plus it squared, and then times, say, m over n to the it dt. So that would be an example of a twisted moment, or sum over chi mod q for primitive chi's, maybe something like L half chi squared times chi of m for some integer m. So everybody can see this okay and hear me okay? Yeah?
Yes.
It's fine? Okay. Right, or maybe if you had maybe if you're summing over say fundamental discriminants, maybe L half chi d quadratic characters, maybe the first power or the second power times chi d of say some L, or maybe you're summing over F in some space of new forms, hk of q, something like that, and then you have maybe summing with the harmonic weight L half f, again, to maybe just some power, and then times lambda f of L. So these are kind of the situations that'll come up in the talk. And so these are your moments, but they're twisted by, one of the Dirichlet series coefficients, or maybe two of them that are in your family. So here we might have chi of m. I should put maybe chi of m, chi bar of n, more analogous to the zeta function case. And after we know now, we sort of attach a symmetry type to different families, sort of based on what we know from random matrix theory and from work of Katz, Sarnak, and things. And so these would be unitary examples, and this would be symplectic, and this would be orthogonal. And we know that the statistics of the families, like the large values, the moments, the way the zeros behave, things like that, are dictated mainly by the symmetry type, but also to a certain and to a lesser extent by the actual family. Mostly, the actual family gives you sort of differences in arithmetic constants that can arise, especially to do with large values and moments. But the main sort of statistics are really dictated by these symmetry types. Anyway, so this is going to be the subject of the talk, and I'm interested in this for several reasons. One, if you want to study zeros, then you usually, zeros are either zeros or non-vanishing. Then quite often you'll look at moments of L functions times a mollifier. That means times an auxiliary polynomial that's multiplied on that has coefficients that kind of imitate the inverse of the zeta function or the L function. So they have Mobius sort of coefficients in there. And if you're looking at large values, then again, you want to do moments multiplied by a polynomial, but now you want to sort of amplify the large values. And so you take coefficients of your auxiliary polynomial that would sort of make the large values, kind of exaggerate the large values. And that enables you to study, subconvexity, things like that. Okay. So now, so I want to just show you some pages from the paper that we wrote in Urbana back in 1981. So Heath Brown actually came over and visited at the same time. I think he was only there for a month or 6 weeks or something, but we got him involved in this project as well. And this is right after my thesis, which I had worked on Levinson's method. And like I said, for studying zeros, I was interested in critical zeros on the half line. And so an important thing was to be able to do complicated integrals like the one here, the integral of zeta, mod zeta squared on the half line multiplied by an auxiliary Dirichlet polynomial, in this case with coefficients little a of m, and the length of the polynomial is capital M. And like I said, for studying zeros, you want to look at mollifying. So your A of m will be mu of m or mu of m times some kind of smoothing polynomial. And you don't, in Levinson's method, you don't actually integrate on the half line. You need to put in little shifts, integrate slightly off the half line, and to be able to carry out his method. But what turns out to be absolutely critical in these calculations is the length of the polynomial. So how big can you make m? And so the whole thing is to try and make m as big as you can. And so that's the goal. Anyway, so we studied this with that in mind, trying to be able to get a large m. Now, in Levinson's method really worked for m equals t to the 1/2. So that's sort of the kind of natural place to go. I mean, there have been earlier works, Selberg and things like that, but before Levinson, it hadn't really been critical to try and get a large value of m. And so he worked hard at that. And kind of the natural thing that comes out is that you can take m as around square root of t to the 1/2 minus epsilon. So we studied this just sort of in general with general coefficients. And we came up with this theorem that here's a formula for what that integral looks like. So we're calling I is that integral, and our theorem is that I is equal to this sort of combination of this sort of bilinear form in the A's. You have a GCD, and you have log and 2 gamma, and then an error term script E, which is sort of in 2 pieces. One of the pieces, E1, is just t over a large any power you like of log. So that's sort of fine. And for arbitrary coefficients, E2 is can be bounded by m squared times t to the epsilon, which indicates that the size of I is around t, or depending on what the a's are, t or t log t or something like that. In general, we have m squared t to the epsilon. That more or less corresponds to Levinson, what Levinson did. And we just have this sort of for general coefficients. And then if something called Hooley's R star conjecture is true, then in general, you can get up to, you get an error term m is m to the 7/4 times t to the epsilon, which means you could take m equals t to the 4/7. So that would be a little bit bigger. And R star, let me see if this works. R star is something like summation R less than or equal to x e of, let's see, I haven't thought about this. I'm probably going to get it wrong, but something like if you sum R bar is the inverse of R mod Q, so sum over R and Q co-prime up to X, then basically you get square root of cancellation right away. Maybe you can put another variable in here. Anyway, that's the R star conjecture. So it's about cancellation of incomplete Kloosterman sums that you get square root cancellation right away. Very difficult question. And then this was sort of the main point was this next line that if A of M has the shape mu of M times a smooth function F, then we could get E2 is M to the 17/12 times T to the 1/4, which turns out to give you then an asymptotic formula in the case that that T goes up to 9/17. And the whole point was to try and beat 1/2. And so we did using sort of Vaughn's identity or Heath Brown's identity, whoever's identity you want to call it, for Mobius was kind of a key part of that thing. And then bounds for Kloosterman sums. Well, the Weil bound comes into this whole thing. But we conjectured something which so then this D here is in the case that AM equals 1, well, then you can actually just use your knowledge of the fourth moment of zeta to prove that that formula is actually correct with M all the way up to T to the 1 minus delta. So that's a simple example where you just take AM equals 1, where in fact our formula works for M all the way up to T to the 1 minus anything. And so we made a conjecture. That in fact that our formula should hold no matter what AM is all the way up to T to the 1 minus delta. And also, we noted that in the case AM equals 1, that the formula fails once M goes past T. So if M is T to the 1 plus delta, then the formula is no longer true. The average changes its shape once M passes T in general. But anyway, so we have this nice conjecture here, and it would be good to prove that conjecture because, among other things, it would imply Lindelof hypothesis. If anybody wants to interrupt any time and ask any questions or make any comments, please feel free to. I don't mind. Just speak up. As a corollary, you take AM as mu of M times 1 minus log M over log big M. So mollifying the zeta, you really need to have a smoothing factor in here. If you just put a mu, you don't get such nice results. But if you have a smooth factor here, then you get this sort of nice if m is sort of t to the theta, then you have 1 plus 1 over theta. And so you can sort of visibly see that as m grows, this decreases. And ideally, what you would like would be to have m go to infinity. And then you would sort of get perfect, kind of mollification of zeta and have the integral of zeta times this thing really is getting close to t. And so that would be nice. We gave an explicit bound for the sum of the distances. You take all the zeros that are to the right of a half up to height t, and the total sum of the horizontal distances is less than 0.085 times t. And then so here we mentioned the application of to zeros. Now we didn't work our formula out for all of the with the shifts that were needed that would have allowed us to do to apply this to Levinson method, but that was really just a technical thing that we could have done easily. And you see, if so, the when m is t to the 1/2, you can get 36% of the zeros on the half line, and with the 17/9 that the three of us got, we could have got. If we'd worked out the details, we would have had 38%. So morally, we had 38% of the zeros. And if Hooley's R star conjecture was assumed, then you could get up to 40%. And from our conjecture, you would get up to more than most of the zeros, 50%. Okay. All right. So a few years after that, I used the work of Desier and Ibanez, and actually could get extended the range to m equals t to the 4/7. That's in the case of mu, not in general. So it's mu of m times smooth. Okay, and then with that, then was able to get 40% of the zeros on the half line. And then that's been improved a couple times since then. The current record is 5/12 by those four authors: Pratt, Robles, Zaharescu, and Sandler. Now, that question I sort of highlighted a second ago, can in that one formula, could you let m go to infinity? Well, in the case that am equals mu of m, with capital M as t to the theta, David Farmer made the conjecture that, so we had observed that you can take, it doesn't work to take m bigger than t for any set of coefficients am, but in the special case mu of m, he made the conjecture that you could take theta as big as you wanted and still get still maintain that the asymptotic formula that comes out. So the conjecture that we had now for, but in the case am equals mu of m, you can take as big a theta as you want. And then he called that or it became known as the theta equals infinity conjecture. It was the thing that led him to originally to make the original kind of beginning conjectures, the ratios conjectures for like averaging 2 zetas over 2 zetas, like doing an average of integral 0 to t zeta half plus alpha plus it zeta half plus beta minus it over zeta half plus gamma plus it, not a 0, zeta half plus delta minus it dt. So a conjecture, so this would be the ratios. And David made a conjecture for how this thing should behave, at least the main term of it. And that is sort of began the study of ratios and the ratios conjecture. Another kind of nice thing is that the theta equals infinity conjecture. So morally, we thought, oh, that needs to imply RH because you're getting sort of perfect mollification, right? As I mentioned, when theta gets larger and larger. But to actually nail that down, it takes a little bit of work. And Sandro Bettine and Steve Gonick showed that. And then later, Sandro and Fai-Chandi and Max Rajivi proved that for arbitrary coefficients, you can take your m slightly larger than t to the 1/2 arbitrarily. So this is sort of 1/2 plus, I think it's 1/66 is what they got, just in general for any old coefficient a of m. So that was kind of nice. The t to the 4/7 that I mentioned at the top of this screen, using results of Desier and Iwaniec, one of the things was that one of the ingredients was actually the average of a fourth moment of zeta times an auxiliary polynomial of, this is in this case of length t to the 1/5. They proved an upper bound for that using their famous work from Inventiones. And that was a key ingredient that allowed us to get up to, or allowed to get up to t to the 4/7 in the zeta squared case. Nigel Watt improved that t to the 1/5 to t to the 1/4. And these are upper bounds. And then Chris Hughes and Matt Young gave an asymptotic formula for that, for an arbitrary polynomial of length t to the 1/11. And in very recent work, Sandro, Fai, Zhenan Li, and Maxime Rajivi now have an asymptotic formula for integral zeta to the 4th times m squared with arbitrary coefficients that works all the way up to m equals t to the 1/4. So it's quite nice, quite a nice piece of work. And one would think that should lead to improvements for zeros on the of zeta on the critical line, but so far it hasn't played. I mean, despite the fact that the original Desier-Iwaniec was so important, this hasn't played quite as significant a role. And but it may just be because nobody's figured out a good way to use it, and so it would be nice to try and do that. In 2018, the CIS, that's me and Iwaniec and Sound, their origin, using the something we call the asymptotic large sieve, we're able to do the analog of actually prove the conjecture from that original paper of Balu and myself and Heath Brown. In the case when you average over Q as well. So this would be sum over Q less than Q, sum over chi star primitive mod Q L of 1/2 chi squared times sum m less than or equal to m chi of m a of m squared. We proved the analog of that formula for m all the way up to m can go up to q to the 1 minus delta for any delta. So it's actually true there. And that has some nice applications. One is that we can now say that at least 60% on average of zeros of Dirichlet L functions on the critical line. So you average over all the Dirichlet L functions, mod all the primitive L functions, ls chi mod q primitive and q up to big Q. Take that whole collection of around big Q squared L functions, and count count how many zeros they have up to, well, a pretty small height, but it's a height that's increasing with Q. And at least 60% out of that collection of all the zeros, at least 60% of the total number are on the critical line. So anyway, yeah, and now we actually, it's actually sort of important in some ways that we have the analog of the BCHB conjecture, or that to get up to 60%, because our mollifier is now no longer just mu times a smooth thing. It's a more elaborate mollifier that Feng found back in around, shoot, I can't remember when that was, 2007 or something? No. Yeah, anyway, it's a more elaborate mollifier that it's kind of like, you're doing Levinson's method. So you're integrating not really just zeta, but like zeta prime or some linear combination of derivatives of zeta, and not on the half line, but slightly to the right of the half line, you know, one half plus some constant over log t. And so now, if you think your mollifier is trying to be the inverse of the thing, some partial sum, some smooth partial sum of the inverse of the thing you're trying to mollify, well then it's no longer just mu. You're taking, you want to know kind of, well, what's the inverse of, zeta plus 1 over log times zeta prime plus 1 over log squared times zeta double prime times some constant, etc. And you find that it's not just Mobius, but sort of, sort of a convolution of, or maybe a convolution of a couple Mobiuses, something or other like that. And so it's not quite so clear how, about the theta equals infinity conjecture and things like that. And so a lot of stuff doesn't quite work. And so we really did want to have to be able to use Feng's mollifier to have general arbitrary coefficients in this formula. And so then that gives us up to the 60%. And by the way, even I think this is true, that one ought to be able to go up to, even with Feng's mollifier, one ought to be able to go up to m equals t to the 4/7, which I believe would give an improvement even over that 5/12. I have to check, but I think that's right. So I don't think in the 5/12 result that I mentioned of Pratt and Robles and Zaharescu and Zeinler that they are taking a mollifier of length t to the 4/7. I think it's slightly shorter, but I could be wrong about that. Anyway, okay, so now these twisted moments, there's a couple, there's sort of a few other reasons I'm interested in them. I mean, they're obviously very useful for applications. I hopefully made that clear. But they're really important kind of structurally as well. And there's some funny things that go on. And so I want to kind of explore those themes a little bit. And one is that you can sometimes get kind of exact formulas for some of these twisted moments, which is a little bit surprising maybe. And, excuse me, two is that sometimes you get kind of a reciprocity formula, which is kind of completely unexpected. It's not something that's not obvious at all from the original structure of the problem. And so there are, I don't know, a couple of examples where that actually happens, and where that might, well, it's already been useful, but it's not, I think we don't really understand exactly how useful it could be. And so I think that's something worth keeping in mind. And so anyway, so I want to go back to this work of Balazard and Sayas, which really is sort of translating into what I would call sort of classical analytic number theory, an equivalent that Berling found for the RH. Okay, so basically they kind of take a Mellon transform of Berling's stuff and come up with this. And I have to say, before I saw what Balazard and Sayes had done, I wasn't that interested in Berling's equivalent, but with the Balazard-Sayes thing, it made it look like, well, you just need to mollify zeta in a really good way, and then you're all set. And there was an important piece in that by Baez Duarte that made Berling's stuff, the support sort of the test functions in Berling's work go to, I don't know, integers instead of real numbers. But yeah, anyway. And then Vas Unions gave a really nice formula for an exact formula for the integral that they have to evaluate. And so that's the first example of sort of an exact thing. And then Sandro and I found a reciprocity formula for this, which is sort of an unexpected relationship then between sort of the twists of zeta by m over n and by n bar over m, where n bar is the inverse of m. So let me sort of explain that. Okay, so here's Vas Unions' formula. So he has this sum v of hk. Here are the double brackets. Oops, wait a second. Double bracket x is just x minus integer. Wait, is that what it is? Or maybe with minus a half? I forget now. Sorry. Maybe, oh yeah, sorry, I forgot. Okay, maybe with a minus a half. Yeah, otherwise it would just be fractional part. Yeah, I think it's x minus. Okay, anyway, so you have this sum, and it kind of looks like a Dedekind sum, right? If you had a Dedekind sum, you would either have both of your arguments would be in the double parentheses, or else both would be cotangents. Okay, well, here you have one sort of double parenthesis and one cotangent. Anyway, that's the Vas Unions sum. And here's the twisted moment of zeta that's in question. It's a little bit different from what we're normally looking at. We're usually focusing on the interval from 0 to capital T, whereas this, because of this weight here, really sort of focuses on, well, what's happening down near 0 in some sense. But nevertheless, it's a twisted weighted average of zeta. It's twisted by h over k to the IT. And Vas Unions proved really a beautiful formula that, in fact, a beautiful exact formula for that twisted average. And that's this here. So that's quite nice. And the connection, the Balazard-Sayes connection to Riemann hypothesis is that RH is true if and only if this limit is 0, where you take the inf over Dirichlet polynomials of length n. I know I switched from n to. You take Dirichlet polynomials of length n and try to make the average of 1 minus zeta times that polynomial, the mean square of that with this weighting function, make that as small as you can. Make that, yeah. And so that is, if you can do that, then you get RH, and now you've got an exact form. If you expand out this, square out the integral and just integrate term by term, and then use Vas Unions formula, then you just have the simple bilinear form that you have to prove has that you can make go to 0, and you're done. Nothing to it. Okay, well, it's not quite that simple, but okay, but so then Sandra and I found a reciprocity formula, which is on this slide. So this is with Sandra Bettine and me, and so we sort of switch the where the H is, right? In VHK, you had the H back over here with a double parentheses, but if you put the H over on the cotangent, that can be accomplished just by a change of variable. A goes to A H bar, and then you can remove the double parentheses because A over K is smaller than 1. And so this is a thing we call C of HK. So also kind of looks like a Dedekind sum, but it's just, it's just minus V of H bar K. And what we discovered is that, well, what we discovered is this, that C of HK times H over K plus C of KH minus 1 over pi K minus log of H over K is an entire function of H over K. So so that was quite surprising and unexpected that happens. And of course, we were very excited about it because we thought, well, this is going to, open the door for proving RH. We just need to figure out how to use this in that Balzard-Sayas example, but it didn't quite work that way. Yeah. So anyway, this G of Z has this expansion with G of N's being pretty small. And we did find some nice applications of this. One is to a Voronoi formula, kind of a generalized Voronoi formula that allows your test function to have support at the sort of at the origin. And so we like that. Here's an example. In the case that, say, Z is 1 minus e to the minus delta. So that's around, that's around I delta, I guess. We have this where this is, there's asymptotic formulas, right? So then you'd be looking at an asymptotic formula for summation D of N e to the minus N delta. And you can write out an asymptotic series for that, but it's a divergent asymptotic series, right? In powers of delta. But this is an exact formula that converges very nicely everywhere. This term here is like summation D of N e to the minus N over delta. And delta is small, so N over delta is huge. So that converges super fast. And this thing, the coefficients C of N, again, are small, e to the minus square root of N. And so here, this gives an exact formula for an exact sort of Voronoi formula that's convergent in a region where the usual Voronoi is not. We use that to give an exact formula for zeta, now weighted in such a way that the mass you're looking at is at sort of 1 over delta. This is the W delta T is like an e to the minus delta T. And again, you get a formula that it's an exact formula that converges quickly, can be calculated super quickly. These U's are Chebyshev polynomials. The point of the AMs are really small, so this all converges. Everything all converges here super quick. So you can actually calculate that very quickly. Okay, so now I want to turn to, let's see how we're doing. Okay, mean square of Dirichlet L functions. Okay, so twists of the family of Dirichlet L functions. So when we were looking at moments of general families, I was trying to look for error terms and make sure that sort of the recipe thing that we had found kind of worked in all the families that I knew. And so I was looking at just the family of mean square of Dirichlet L functions. And so studying Heath Brown's paper, now he'd given an average, an asymptotic average actually using that formula for d of n e to the minus n delta, but the asymptotic formula. But it was for all. And when I restricted to primitive ones, then it got a little bit more interesting. And I actually found a kind of reciprocity formula for twisted L functions. And then Matt Young refined it, and then Sandro sort of turned it into an exact formula. So here's sort of the original reciprocity formula that I found. We're averaging L 1/2 chi squared times chi of A. We call that MAQ. Now this is scaled a little bit differently. It's scaled with a kind of a 1 over square root of Q scaling. Okay, so the size of it is going to be around root Q or so. Anyway, here's the reciprocity formula. If you take MAQ minus M minus QA, then you get sort of all this main term. And this gives an asymptotic formula that goes beyond the range of what you would normally get for this. Here you would expect the asymptotic formula to only work for A up to square root of Q. But in fact, if you take both of them together, then you can get A up to Q to the 2/3. And so it kind of extends the range of what you know about that twist by including sort of the other term. And then Matt made it much more precise. And if you write his exact formula, if you write his error term like that, just if you calculate his error term, you see that it kind of looks sort of interesting. This is, And in fact, then Sandro showed that error term is in fact a continuous function. E of A over Q is actually, E of A comma Q is actually E of A over Q is a continuous function. And I think I'm going to skip through this a little quickly, but he gave an exact formula for, so MJ star is sum over chi mod Q twisted by chi of A, but not just at 1/2, but it's actually a sum of L, but at half minus J and half plus J, with an extra sort of zeta term added in here. And well, this is a little complicated, but anyway, he gave an exact formula for M0 here, which is kind of nice. But one of the things, sorry, I know I'm just sort of skipping through that, but one of the things is that in this reciprocity formula, you can sort of repeat it. You're looking at MAQ, and then that gets related to MQA or maybe M minus QA, but then you can reduce Q mod A, right? Because it's just a chi of Q, but chi mod A. And oh, by the way, Q is supposed to be prime and A was supposed to be prime in those previous slides. And then you can apply the reciprocity formula again. So you go back and forth, back and forth. You keep on reducing the thing, like the Euclidean algorithm or something. And so in fact, this second twisted moment of L, Sandro writes in terms of the continued fraction of A over Q. If the Vj is the jth partial denominator, then you get an exact formula like this. And that then, one of the things, so that's interesting, and it would be really interesting to try and apply this sort of further. But one of the things that comes out of this is that you can actually then see when M0AQ might be particularly large. So it kind of explains a little bit of this thing where you see sort of the large values that kind of occur when A over Q is close to a fraction with a small denominator. So that sort of aspect of it can be made sort of explicit from this continued fraction expansion. And in fact, it shows that, so here's a nice sort of clean formula for this in terms of continued fraction expansions. And it shows when this thing is large. And so one of the points is that, so point-wise, for individual A, you can't really the thing is does not behave as well as you might like. So restrictions that sort of came from looking at this thing individually, it turns out you can be well, if you put in general coefficients and average, then on average the terms are small, but there's some individual ones that are quite large, is what I'm trying to say. So yeah, I didn't say that very well, but so this can be used to analyze especially large values of these twists. And the large values are much larger than the individual large values are much larger than when you average over all twists, like put in a polynomial and do sum over chi L half chi squared times a polynomial squared, then you get much better. I mean, I guess we sort of knew that, but this sort of really brings it home that that's a phenomenon. Okay. All right. Well, okay. So quadratic L functions. So Sound gave a formula for that. He was studying non-vanishing of these of quadratic L functions at 1/2. That was sort of the Challa conjecture. That these L functions, quadratic L functions never vanish at 1/2. I think, yeah, and I mean in general we don't think any Dirichlet L functions vanish at 1/2. I don't know, I can't remember if that was part of Challa's conjecture or not, but certainly the quadratic ones. And Sound proved at least 7/8 of these don't vanish. And then he and I used later on these twisted L functions, but with shifts and things like that, to show that in fact for 1/5 of quadratic L functions, you don't get any zeros, any real zeros to the right, any positive real zeros of the L functions. Yeah. Right. Okay. Let's see. So what time should I be stopping here? At 50 past, or what? What do you recommend? Somebody, Kaisa?
Well, I think it's okay if you go until 5 to 55, and then there's
55.
Time for a couple of questions after that.
Okay. All right. Well, all right. So yeah. So in general, so we have a recipe for moments of L functions, basically in any family. And there's an analogous twisted recipe that's not really written down anywhere. And it's just sort of still coming into shapes, still being formed in some sense. And one of the issues is not quite sure what error term we should expect, especially as a function of the twist. But here's a recipe for moments of quadratic L functions. Well, twisted. This should be. Yeah. So LA S chi D is a product of L of S plus alpha chi D over alpha in A. A is some set, so it's just a product of all those, and then we have a smooth test function, and then that product, and then we're twisting by chi dl. So if L is 1, then we're not twisting. And in order to write down sort of what the recipe is, it turns out this is the critical function here. Some n equals square tau a n over root n. Of course, I could just put in m squared here, but I like to write it this way because then, in fact, when we twist it, you don't have to change the function very much. And so the critical function when you're twisting is some, well, n and d are coprime, and then n times L is a square. So when you twist, the way that you change the basic function is you include this condition, not just n equals square, but n times L equals square. So it's a pretty seemingly kind of minor thing. And then this is the recipe that we have, that if you average this, then basically what you get is you get these swap terms. You get a sum over subsets of A, be a subset of A. These are the factors from the functional equation, and then here's your basic function B super D of. Now it's A. You take your set A, you throw out the elements B that's in your subset, and you add back in the negatives. So you replace all the things in B by their negative. That's what this A minus B plus B super minus is. And we conjecture an error term L to the 1/2 D to the 1 minus delta. This we're not so sure about what that should be exactly. For zeta, we would have put out D to the 1/2 plus epsilon there. But for quadratic L functions, there's some extra terms that can come into this, as discovered by the multiple Dirichlet series people, Diaconou and Zhang and Hofstein and anyway. Okay, so with Brad Rogers, we proved this basically in the situation where we replace our quadratic L functions by a partial sum, a sum up to n, where n is d to the eta, and eta can go all the way up to 2. And we get the exact analog, assuming the Lindelof. We basically proved that twisted formula. So that actually works. Okay, sorry, trying to keep track here. Okay, right. There's an exact formula Ivanets and Sarnak found for twists of orthogonal L functions. Kowalski, Michel, and Vanderkam have studied this for the fourth moment case. And then recently, Blomer and Kahn found a very exotic reciprocity formula for twisted fourth moments here. So I won't describe that. But I wanted to just mention, if I can first, what happens in the random matrix case. So this is the recipe for zeta, and you have this basic function here for the twisted zeta. Right, twisted zeta, that's here. Oh, I see. Okay. So sorry, those guys weren't supposed to be there. Yeah, that's a basic function for zeta. And then for twisted zeta, you just have to change your condition a little bit to that. And in random matrix theory, what we found is, well, if you take, the coefficients for characteristic polynomials, if you call those the secular coefficients, then what Sig Baliut and I found was a formula for twisted moments in random matrix theory, twisted by these secular coefficients. And the thing is that it comes out a very nice analog with what you have for the Riemann zeta function case. We have this analog of the tau function that we define for random matrix theory. And the when you twist, you get sort of this function, which involves sort of multiplying by the taus, which is kind of like what happened. Oops. Oh, I guess that's on the next slide. Sorry. What happened here, the BMN. So yeah, so trying to compare those two things. And we're trying to make this, we're trying to take this a step further and have a random matrix version of sort of the papers that Keating and I have been working on that give an approach to the general recipe from convolving twisted recipes together. And that's where we're sort of headed. Okay, thank you. Happy birthday, Balu. Happy birthday tomorrow. Thank you.
Thank you very much for this interesting talk. If you have some questions or comments, please put your mic on and ask.
Hello, I have a question. So in the mollification, of zeta function, you consider basically your mollifier square and so zeta even zeta square. So
Right.
as you see the Selbach type mollifier, they are basically mollifier power 4.
Right.
So this case actually I did not find anywhere the asymptotic result. So can you say something?
Right. So yeah, you can work all that out. And I tried to do that at one point. I think you get slightly worse results, but they're not quite as bad as sort of has been reported. I think in Selberg's, proportion of zeros on the half line. I mean, somehow by having to do a fourth power, it sort of ties your hands behind your back a little bit and restricts what you can do. But I think you still get decent results. I don't know if that answers your question, but yeah, you can do that.
So in this case, the mollifier, heard about the mollifier length?
Oh, you should be able to get the, oh, can you go longer with that mollifier? I do not, I do not know. I mean, Desier Ibanez look at that zeta squared times a product of 2 squares of mollifiers. Yeah, no, I have not thought about that. I don't know.
No, thanks. So another question, sorry. If you saying about this reciprocity law for these central values twisted by character, so if you consider the your cast form case, I mean degree 2 setting, and if you similar type of study, the this reciprocity formula holds for degree 2 setting.
In the for orthogonal twisting, is that what you said?
Yeah, I'm saying yes. I mean, you mentioned already initially the F belongs to HKQ and L half F power 2 lambda FL.
Right. So yeah. So I don't know. I mean, yeah, I was curious about that when I was preparing this talk. Okay. But yeah. So the Ivanit-Sarnak is for level 1. They mentioned something about level Q, but they never mentioned a reciprocity formula. And so, you know, Blomer and Kahn get it for 4th power. So I don't know. It seems like there ought to be one. There might be, and especially since Ivanit-Sarnak have an exact formula. So yeah, I mean, I think that would be worth doing for somebody to do twisted mean square. That's what you're asking about?
Yes.
Yeah. As far as I know, nobody's done that.
Oh, thank you very much for your nice and informative talks.
You're welcome.